Hey everyone, it's Mr. Canfield. Today we're doing improper integrals. So you've got the proper integral that looks like this, and then you have the improper one that looks like this, but here's the proper integral with his top hat, and here's the improper integral with his, with his backwards baseball cap. Whoa, that's an improper integral. They pay me to do this.
Not specifically that.
All right. So the big deal with improper integrals is we're going to have one of the bounds be infinity. That's what's so improper about them. So yeah. So basically what's going to happen is we're going to do the integral normally, and then we're going to have to take a limit to find out what the answer is going to be. So you basically have two options with an improper integral. So like let's say we're going from 3 to infinity of some function. This is the area from 3 to infinity underneath a function. So if you were to think about, if we had a function where it was just like this, getting bigger and bigger and bigger as we go off to infinity. So like here's 3. If you look at that area, this is some, like let's say this is 1. So like at 3, you start with an area of 1. As we go, each little bit of area that we pick up from 3 off to infinity gets bigger and bigger and bigger and bigger and bigger. So if we were to add all those areas up, I hope that it makes sense that we would have some infinitely large area here. But let's look at a situation where we don't get an infinite area. So what if we had something like this? And pretend that I can draw and pretend that this like asymptotically approaches 0. So now, and we'll just say, here's 1 again. We'll say at 3, it's at 1. But then we wind up adding these little tiny pieces, and the pieces get smaller and 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 smaller. So it's actually possible that this infinite amount of area here adds up to a finite number. So we call the areas that go off to infinity, we call these divergent, and these we call convergent, just like a limit that converges. So so let's just kind of look at his examples and kind of go through stuff. So the graph to the right shows the velocity function described above. So he talked about like a car driving along or something. All right, so it says, suppose you're driving along the highway at 100 feet per second. It's about 68 miles per hour. So your velocity is given by this function where t is seconds and v of t is in feet per second. According to the model, the velocity approaches 0. So like, yeah, if you look at that, it says e to the negative 100 e to the negative 0.1 t. As t gets bigger, our exponent gets more and more negative, more and more big negatively. So this turns into e to the negative infinity as we go off to infinity. And e to the negative infinity, we say in limit terms, is 0. It approaches 0. So according to the model, the velocity approaches 0 as time approaches infinity. This never actually equals 0. So in a way, we could say your car never actually stops. It just gets slower and slower and slower and slower. Those of you in physics, we have this is like an ideal situation. In physics, you would also have a couple other factors that would eventually make it stop, such as friction, energy lost due to heat transfer, those kinds of things. Eventually, it will lose enough energy and stop. But we're saying, from a pure math perspective, if we have this one function, this never actually stops. So would the distance you travel approach a limiting value, or would it increase without bound? So we're going to look and see this velocity function. Since you never actually stop, do you manage to make it an infinite amount of distance, or is there some kind of limit to the distance? So if you increased without bound, that would be a divergent situation. If you eventually, like if there's some limit to the amount that you can get, that would be convergent. All right, I think we've talked enough. So we've got a slightly altered version of it over here now. We see our distance from 0 to b is 1,000 e to the negative 0.1 t dt. So I think he makes a mistake in his work here. But let's look at some of these options. This is worth kind of numerically examining. So what variable are these bounds in? X, Y? No, t, because it says dt. So I'm going to drop this into y1 so I can use calculator shortcuts instead of having to retype things over and over again. I'm going to use x for my variable because that's, we have that dedicated button for it. So if I go in and go to the integral and I go from 0 to, oh, you know what? I actually could go to b. We'll talk about how we can define that in a minute. And then I can actually use alpha f4 and use y1. So saves me some typing. Let me define b. So as b approaches infinity, oh wait, so at 10 seconds, let's see, so you go, I type 10, and then see this button STO, it means store. I can store 10 to b. If I do that, and then I go up and use this. Yeah, so he made a baby mistake somewhere. If you look in his work, when he did the integral here, he forgot about the 0.1, and he treated it as a -1. So, but it's not going to change a whole lot. So at 10 seconds, we're there. What about at 100 seconds? Is it because she's wearing a huge vest?
Look at his outfit.
All right, guys, we gotta.
I don't want to be in this.
Well, I was making it so you could just show her. Oh dear. Oh dear.
Look at these hedgehogs.
Hedgehogs. I was trying to make it so you could just kind of put her into frame without having to be in frame yourself. All right. So anyway, so if we made b 100, try it again. That's fun. 9.5. Well, what about 1,000? Oh. What about 10,000? So the more tech savvy among you probably are understanding this value of 10,000 that we're getting out. Is not exact. There's probably a whole string of decimals, but it's so close to 10,000 that it winds up being round off error, and it doesn't actually show us. So this is probably 10,000 point, a whole bunch of zeros and then something. So we basically have this limiting factor of 10,000 feet. It's never going to actually make it to 10,000 feet, even though it looks like it here. It's got a round off error. If you remember a minute ago, it was at 99. It was, so 100 seconds in, it's already so close to 10,000 feet. So we're going to kind of skip this question here, but this idea of this is approaching some value hopefully is evident. And if we look at the graph of this, you know, let's get a meaningful window here. Let's go from, let's go to 100 seconds, and then vertically we'll go from, I always put the negative ones just so that it goes a little bit past the axis so that it will see the axis. Oh wait, it goes all the way up to 10,000. So let's do like 20,000 and see. Let's see what happens. Oh wait, I'm thinking about it from an addition standpoint. I think we actually just need 10 here. So this is, each of these is like the individual instance of our velocity. Remember that the integral adds up the area that we have underneath this. All right, so you might be wondering, so how do we actually do these problems? Yes. So basically what we're gonna wind up doing is we're gonna say, okay, we're gonna take the limit as b goes to infinity. This is a normal improper integral here. Why we pick b, I have no clue. But that's what you use. That's what I used in high school. That's how improper integrals work. So now we just integrate this. So this we would need to use u substitution to integrate properly. So our du is going to be negative 0.1 dt. This is going to be du over negative 0.1 is going to be equal to dt. So when we do our replacement here, we'll get limit as b goes to infinity from 0 to b of 1,000 e to the u du over negative 0.1. And 1,000 divided by negative 0.1 moves the decimal place over 1, right? That makes it negative. So it's negative 10,000. And I'm going to pull that negative 10,000 out front. So if we look at this integral, we can actually take this integral now and get the limit as b goes to 1,000, or b goes to infinity of negative 10,000 times e to the u integrated from 0 to b. And let me drop u back in. U was negative 0.1 t. So if we look at this, this winds up being e to the negative 0.1 b minus e to the negative 0.1 times 0. And that winds up being e to the 0, winds up being 1. So now we just have to figure out what's the limit as b goes to infinity. It's going to be e to the negative 0.1 times infinity. What's 0.1 times infinity? And what's e to the negative infinity? So as b approaches infinity, our actual integral approaches 10,000. So let's just do some examples. I can't remember if I already said this. This is a, sorry about that. This is a one-off unit. So we're going to do a couple of things today, and then that'll be it for it. We want to figure out whether or not this is going to be some kind of convergent integral. So I'm going to do this without graphing to determine whether or not this can converge. And I'm going to use,
It looks so bulky in the back.
I'm going to use a chart, not a chart, like a discussion tool. We've got like different power levels. We've got x to a power. We've got a number to the x power. We've got x to the x power. We have x factorial. So then we also have x to a power that's like underneath 1, so like the half power or something like that. We also have ln x, and then we have trig, like sine or cosine. And each of these, as x approaches infinity, kind of has its own like version of infinity. Some infinities are actually bigger than other infinities. And if you're like, no, that's not true. Well, think about this. Let's take x versus x squared. As we approach infinity, they both approach infinity. But here's the thing. This one approaches infinity. This one approaches infinity times infinity. This one is infinitely larger than this one. Let's compare that to x to the third. X to the third is actually infinitely larger than x squared at infinity. So one more power of x winds up being infinitely larger than the previous power as we approach infinity for these. So it's a little bit hard to tell, but what about like 2 to the x versus 3 to the x? So 2 to the x and 3 to the x. Well, 2 to the x is 2 times 2 times 2, an infinite number of times. 3 to the x is 3 times 3 times 3, an infinite number of times. All right, so these one I'm going off to infinity, and so this is an infinite number of 2s, an infinite number of 3s, so obviously a 3 is going to be bigger than a 2. As we go out to infinity, they have some kind of relationship with each other, but how about 2 to the x versus x squared?
Oh.
Did she just sneeze on you? Ew.
Drinking her bottle.
Oh, maybe.
Milk went everywhere.
So let's think about this. If we start with 2 to the x, let's try 1. If we try 1 here, we get 2 to the 1, that's 2. 1 squared is 1. Let's try 2 now. It's 2 squared is 4. This 2 squared is also 4. Oh, so they're the same. Let's try 3. 2 to the third is 8. 3 squared is 9. So you might be like, oh, this one's getting bigger. Let's try 4. 2 to the fourth is 16. 4 squared is 16. Huh. Maybe they just like, one's bigger, they trade, the other one's bigger, they trade. Let's try 5. 2 to the 5 is 32. 5 squared is 25. Oh no, this one's bigger. Let's try 6. 2 to the 6th is 64. 6 squared is 36. Oh. 2 to the 7th is 128. 7 squared is 49. Uh-oh. Let's jump down to 10. 2 to the 10th is 1,024. 10 squared is 100. What about 100? What's 100 squared? 10,000, right? What about 2 to the 100th? So which one's bigger? One with 30 zeros or 10,000? This 2 to the x versus x squared, this is infinitely bigger in a way that is obscenely bigger. So comparing these x squared, x cubed, comparing them with one another, x to any power, x to some number power is going to lose to just 2 to the x. Like you could pick, oh, well, what about x to the 100th power? Compare x to the 100th power and 2 to the x. So like, let's say 100, right? Oh, 100 to the 100th, that's way bigger than 2 to the 100th. That's true. But what if it's 1,000 to the 100th versus 2 to the 1,000th power? I am guessing that neither of these are going to work in my calculator. Yeah, that overflows. So this is 1,000 times itself 100 times. This is 2 times itself 1,000 times. If you're still not convinced that like that's bigger, we could take 2 times itself 1,000,000 times. 1,000,000 times itself 100 times. I would encourage you to go on the computer and try typing some of these out on a calculator that can handle it if you want to see how astronomically more that is than that. Because our puny little calculators can't handle that many decimals. So if you want to compare those though, both of those lose to x to the x. They also both lose to x factorial. So x to the x would be like let's say x is 10. So x to the x is 10 to the 10th. X factorial means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You've probably seen this before. If you're in stats, you've probably seen it before. So I think we've covered everything we need to for now. I'm going to leave the jury out on whether or not which one of these two actually is bigger than the other. So here's the whole reason I'm doing this. So we get back to this question, this 2a here. We're trying to figure out whether or not this could converge. So what we do is we say, well, I'm going to rewrite this. I'm going to say this is x squared over e to the x just to think about it. As we go out to infinity, this is a number to the x versus x squared. Who wins that fight? This wins the fight. That means that this is going to converge. Sorry, how do I know that? So this wins the fight. So as we go out to infinity, this approaches 0. If the top won the fight, as we go out to infinity, the top would be more and more infinite than the bottom, and so it would approach infinity. So if it was this way, the top wins the fight. So top gets really, really big, bottom not as big, so we go off toward infinity. But we want to find out what this converges to, and so we use an improper integral. And so the way that you're supposed to do it is with that limit notation I did earlier, but you really can just keep infinity as your bound. You're just not supposed to. It's not proper. Let's put the backwards hat on it again. Okay, so that's not a mathematical symbol. That's just me being stupid. So if I'm trying to do this, I think I need to do integration by parts here. And so I'll say u, and I'll say this is dv. I'll just use my table, right? I'll say x squared, 2x, 2, 0, like that. And then I'll say e to the negative x. That just repeats itself each time. But each time, because we have a negative 1x, it's going to be negative, positive, negative. So I'll get negative x squared e to the negative x. All right, let's see, minus 2x e to the negative x minus 2 e to the negative x. And we're evaluating this from 0 to infinity. So first thing, I'm going to plug in the 0 because that's the easy one. When I plug in the 0, that's our second half of the integral, right? So we get 0, 0, and then this. Oh, it's just negative 2, right? Because e to the 0 turns to 1 times the negative 2. So it winds up being 0 minus 2, so it's just going to be plus 2 here, because minus negative 2. So now we got to plug in an infinity over here. So I just took my integral and I plugged in infinities. This is inappropriate or improper. Backwards cap. All right, so this is improper. But the idea here is easy to understand, right? So who wins the fight? Infinity squared or e to the infinity? E to the infinity. So that means that this is going to be 0. Same thing here, infinity or 2 infinities. Whoa, I got double infinity. Well, we have e to the infinity, so that's also going to be 0. 2 versus infinity, also 0. So all this boils down, and our area approaches 2 as we approach infinity. So that's the that's kind of the rub here. So let's just kind of break down what we did here. We took our original problem. First, we made sure that it's a situation where the bottom wins the fight, where it's going to, our terms actually are going to be approaching 0. And then we had to integrate it. And then we just did the integral like we normally do, except we used infinity for our top bound, and we kind of had to think about those from a limit perspective. I guess technically we could have done L'Hopital's rule on each of those, but like, I'm good. You're allowed to kind of feel the answer. So like this one, x over 2x, or x plus 1 over 2x. Who wins that fight? We wind up having infinity plus 1 over 2 infinities. These actually don't deviate from each other a whole lot. This one just winds up being twice as big. This winds up looking like 1/2. So think about this. As we go off to infinity, we approach 1/2. Add up 1/2 an infinite number of times. What do you get? Infinity. So this one is actually divergent. A little bit of a test-taking humor for you. All right, so 4, I like 4, straightforward. So this is just an e to the negative x. Well, if our x squared times e to the negative x converged, this is going to converge too, because it has a 1 times e to the negative x. This is just 1 over e to the x. So it should converge. And if we take the integral of this, beautiful integral here, we wind up getting negative 1 over e to the infinity minus negative e to the 0 that's just 0. This is 1. So believe it or not, the area from 0 to infinity of this shape adds up to exactly 1. So if you can imagine, that little sliver that starts right there and goes all the way to infinity, add up all the shaded region underneath it from 0 to infinity, you get exactly 1. For me, that's hard to believe. But hey, it's true. Let's look at 5. All right, so in this one, we can see that it's a number over infinity as we go out. So it's possible it could converge. So this is x to the negative 2, right? So its antiderivative will be x to the negative 1 divided by negative 1, right? So I could write that as, drop the calculator. I could write this as negative x to the negative 1 from 1 to infinity, which will be, all right, why don't I just write this as 1 over x, right? And do that instead. So I could say this is negative 1 over infinity minus negative 1 over 1. This is, wait, 1 over infinity goes to 0. Negative negative 1 is 1. So this also adds up to 1. Super exciting. All right. Let's look at number 7. 1 over x cubed. Okay, this goes from 1 to infinity again. Gee, I wonder what this one's going to go to. Probably 1 again. It doesn't. All right, so this time, right, this is x to the negative 3. So our integral will be negative 3. Nope, be negative 2, right? And then we'll divide by our new exponent. So I actually could write this as negative 1 over 2x squared. Right? Because that flips down there. So now I can think about this as saying one over 2 infinity squared minus so that's going to go to 0, and this is going to be a half. So this one actually adds up to the area is a half. All right. 6 is more of the same. Oh, no. Different bounds. Negative infinity. So let's see what happens with 6. So, oh, I know. I want to be like, oh, well, it's a simple antiderivative. It's not a simple antiderivative. And this is actually one of our special formulas. This is the antiderivative of inverse tangent. So this is like a weird situation, but if you don't remember what inverse tangent looks like, it looks like the tangent curve looks like kind of like that, not as exaggerated. It looks like that. So the inverse tangent is going to be flipped on its side and flipped upside down. Looks like this. So we've got to figure out what this adds to. So the weird part is we have a lot of negative, we have a lot of positive. And it's symmetric to the origin. So I actually think this actually adds up to 0. So let's look at this. Inverse tangent of infinity minus inverse tangent of negative infinity. So as we approach infinity, inverse tangent approaches an angle. So what angle gives us a tangent of positive infinity? And that's where if we go look at our unit circle, right, inverse tangent winds up being y over x. So we get an inverse tangent of infinity, or sorry, we get a tangent of infinity when we're at the point 0, comma 1, which is pi over 2. Because 1 divided by 0 we could think about as positive infinity. And then we could think about 0, negative 1 as negative infinity. So
Can you help me?
okay, so this result was kind of counter to what I was expecting. It's correct, though. I double checked with the internet, and they agree with me. So, yeah. Oh, it's because we're looking at this shape. We're not looking at inverse tangent. We're not finding the area under inverse tangent. We're looking at the area under this from negative infinity to infinity. Oh, okay. Yeah, so that little blip right there. Okay. All right, onward and upward. So I've seen some disagreement over the years with this one. So a second type of improper integral is in the form of a to b, where f is discontinuous at either a or b. Similarly, if there's a c where it's discontinuous, we can break it up so that there's this k value where it's saying like from one side is discontinuous to the other side. So we're trying to find this area. So I have heard this area called divergent because one of the sides goes off to infinity. I've also seen the argument that this area is 0 because even though they both go off to infinity, they go off to the same infinity. So so if we're trying to find the area from 1 to infinity, that's possible. Wait. Oh. Okay. So yeah, that's the situation for that. I'm going to give you a short version in just a second. All right, I did not just pause and go watch a black pen, red pen video on this. So those of us saying 0 here, if you understand this to be 0, that makes total sense, right? Because it's an infinite area, but they cancel each other out. One's positive, one's negative. We are at a place where we're just going to say, no, we can't figure that out yet, even though I think it's pretty clear with this example that it is actually 0. You have to go to some upper level math. I know we're in upper level math, but there's something, yeah, upper level. There's this guy Cauchy that you learn about. So wait, I thought principal should be LE. Anyway, the Cauchy principal value would be 0 here. I never learned this, but it's in something called analysis, which, believe it or not, what we're doing now is not analyzing according to math people. Analysis is like a deeper level that we go. But anyway, all that to say, to find this integral here, we really have to break it up since there's this discontinuous piece here. We'd have to break it up into -1 to 0 of 1 over x dx plus 0 to 1 of 1 over x dx. And since one of these diverges, we stop there and we say, look, since part of this diverges, we just have to call it's divergent right now. And if you're like, no, if you go through and do the work, Mr. Canfield, you wind up getting infinity minus 0. I guess this one's 0 minus infinity, and this one winds up being infinity minus 0. Or you wind up getting infinity minus infinity as your answer. And if you remember, infinity minus infinity is actually indeterminate. So because of that, we get an indeterminate limit here. And for how much we are going to learn in this course, we're going to say this is divergent. So number 9 is literally number 7 again, so we're not doing it. But if you look at number 10, you might think, oh, that's going to be another one of those fractions, like 1 or a half or something like that. But let's check it out. This is 1 over the cube root of x, which is the same thing as saying x to the negative 1/3, right? So if you integrate that, you wind up getting x to the 2/3, and then you divide by that new power. So this one, when we plug in the 1, we get 3 over 2. When we plug in infinity, we get 3/2 times infinity to the 2/3. The 2/3 is equivalent to the cube root of infinity squared. Wait a minute. That's not 0. This actually diverges. So, turns out if x to the power of n, if n winds up being under 2, no, 1. No, oh, it's between 1 and 2. Oh, I can't remember. So that'd be an interesting exercise for you to do. We're gonna spend more time on this later this year. And for now, I'm gonna pretend that I don't remember, because I don't remember where n is exactly, where this starts to converge and diverge. All right. The area bounded by y squared is equal to all that, and the x-axis is shown here. Find the shaded region. No. All right, cool. We're on to our homework. So, again, this is a one-off chapter. Let's do the evens. So just do the evens. Even Stevens. All right, hope this was helpful. Bye.